Imagine if gravity itself went missing. Deep beneath the Indian Ocean, there's a spot where Earth's gravity is mysteriously weaker than almost anywhere else. This real phenomenon, called the Indian Ocean Geoid Low, or the gravity hole, has puzzled scientists for decades. Here, the ocean's surface actually dips down, pulled less by gravity's grip. For years, researchers detected strange readings in this vast area, sparking debates and wild theories. The gravity hole covers over 3 million square kilometers, big enough to fit India inside, and the sea level is over 100 meters lower than average. But what could cause such a massive gravitational oddity? The answer involves ancient oceans, drifting continents, and fiery plumes deep within Earth. Let's dive in and uncover the secrets of the Indian Ocean's missing gravity. When you hear the term gravity hole, you might imagine something dramatic, like a black hole in space or a swirling whirlpool in the ocean. But a gravity hole is neither of those things. It's not a cosmic vacuum sucking in everything nearby, nor is it a visible pit in the water. Instead, a gravity hole is simply a region on Earth where gravity is a bit weaker than what we consider normal. These areas are subtle, invisible to the naked eye, but they can be detected with precise scientific instruments. If you were to stand or float above one, you wouldn't feel any different. But sensitive equipment can pick up on these tiny changes in gravity, and they're significant enough to actually make the ocean's surface dip ever so slightly in those regions. To help visualize this, imagine the ocean as a giant, flexible blanket draped over the entire planet. If there's something less dense underneath that blanket, like a soft pillow or a missing chunk, the blanket will sag or dip in that spot. That's exactly what's happening in the Indian Ocean. Deep beneath the surface, there's less mass than usual, which means gravity is weaker, and as a result, the sea level above dips downward. This area is known as the Indian Ocean Geoid Low, and it's the largest and most dramatic gravity hole on the planet. The sea surface here is over 100 meters lower than the global average, an astonishing difference considering how flat the ocean usually appears. But don't expect to see a swirling vortex or a gaping hole. The depression is gentle, spread out over a vast area and completely invisible to the human eye. It's only through careful measurement that we know it's there. This phenomenon is a direct sign that something deep inside Earth is different in this region. It hints at hidden processes far below the surface. Scientists believe that the mantle rock beneath the Indian Ocean is either less dense than usual or arranged in an unusual way, which affects the pull of gravity above. By studying this gravity hole, researchers gain a rare and valuable window into the mysterious workings of Earth's deep interior, places we can't reach directly but can explore through their effects on gravity. It's a powerful reminder that some of the planet's biggest secrets are completely invisible, yet they leave measurable fingerprints that scientists can detect and study, helping us better understand the world beneath our feet. The mystery began in the 1940s with Dutch geophysicist Felix Veening-Maijnes, who measured gravity from submarines to avoid the rocking of ships. As he crossed the Indian Ocean, his instruments consistently showed weaker gravity south of India. This wasn't a fluke, the data was clear, something was off. Maijnes had stumbled onto a global anomaly, but at the time no one could explain it. Plate tectonics was still a new idea, and our knowledge of Earth's mantle was limited. All they knew was that gravity didn't match the simple model of a uniform Earth. Later, satellites mapped the anomaly in detail, revealing its true size and shape. What started as odd submarine readings became one of the most significant features on Earth's gravitational map. Maijnes's work launched decades of research into the planet's hidden depths. The gravity hole was no longer just a curiosity, it was a major scientific puzzle, and the hunt for answers had only just begun. Once satellites confirmed the gravity hole's size, scientists raced to explain it. Early theories blamed a thin or less dense crust, but calculations showed that wasn't enough. The real culprit had to be deeper, in the mantle. Some thought a sunken tectonic plate might have dragged down the mantle, creating a divot and lowering gravity, but there was no direct evidence and the shape didn't quite fit. The problem: we can't drill to the mantle, so scientists relied on indirect clues like earthquake waves. For decades, the data was too fuzzy to solve the mystery. The Indian Ocean Geoid Low remained a stubborn enigma, waiting for new technology to reveal its secrets. The answer, it turned out, would be even more dramatic than anyone expected. To really understand the mystery of the gravity hole, you first need to realize that Earth isn't a perfect sphere, far from it. Even though it might look round and smooth from space, our planet is actually full of subtle bumps, dips, and oddities. In fact, if you could shrink Earth down and hold it in your hand, it would feel more like a lumpy potato than a flawless ball. These lumps and bumps are everywhere, and they're not just on the surface. Scientists have a special name for this odd shape: the geoid. The geoid is an imaginary surface that represents where gravity is exactly the same everywhere, like a global invisible sea level. But the geoid isn't smooth because Earth's mass isn't spread out evenly inside. Some regions are packed with dense rock, while others are lighter, and this uneven distribution creates a bumpy gravitational field. Where there's more mass beneath the surface, gravity is stronger, and the ocean surface actually bulges upward, as if pulled by an invisible hand. But in places where there's less mass, like the mysterious gravity hole in the Indian Ocean, the ocean surface dips down, creating a kind of invisible valley in the sea. The Indian Ocean. Geoid low is the deepest dip on the entire planet, a spot where gravity is weaker than anywhere else on Earth. So when scientists say the sea level is about 100 meters lower there, they mean it's 100 meters below this bumpy, invisible geoid, not below the average sea level you might imagine. These strange bumps and dips on the geoid are like fingerprints, revealing clues about what's happening deep inside our planet, far beneath our feet. By carefully mapping the geoid, scientists can infer the hidden landscape of rock, magma, and ancient structures that lie far below the surface, things we could never see directly. The gravity hole stands out as the geoid's biggest signal, clear proof that something extraordinary is happening deep in the mantle, reshaping the planet from within. For geologists and planetary scientists, the geoid is a powerful tool, almost like an X-ray, for peering into Earth's mysterious interior. Thanks to these discoveries, our understanding of Earth has changed forever. We now see our planet not as a perfect sphere, but as a dynamic, ever-changing world shaped by forces deep below the surface. The breakthrough came from Indian scientists Debanjan Pal and Atreyi Ghosh, who traced the gravity hole's origins back over 100 million years. Their research links the anomaly to the breakup of the ancient supercontinent Gondwana. As India drifted north, it crossed over the Tethys Ocean, whose dense floor was forced deep into the mantle. This sinking ghost ocean slab disturbed the hot rock below, pushing lighter mantle material upward. These rising plumes, giant columns of hot, buoyant rock, are like slow-motion lava lamps under the Indian Ocean. The combination of the sinking Tethys slab and rising plumes created a region with less mass in the mantle. That's why gravity is weaker and the ocean surface dips. It's not one event, but a collision of ancient tectonic drama and deep Earth currents. The Indian Ocean geoid low is a scar left by a vanished ocean and a fiery plume. To test their theory, Pal and Ghosh turned to supercomputers. They built detailed models simulating 140 million years of Earth's shifting plates and flowing mantle. Running 19 different simulations, they watched virtual continents drift and the Tethys ocean floor sink. In 6 models, the sinking slab and rising plumes naturally created a low-density zone, right where the gravity hole is today. Models without the Tethys slab failed to produce the anomaly. This was the smoking gun. The ghost ocean was essential. Seismic tomography, like a CT scan for Earth, also revealed real plumes and remnants of the Tethys slab deep below. The computer models and seismic images fit together, finally explaining the gravity hole's origin. It was a digital and geological breakthrough. For the first time, the pieces of the puzzle snapped into place. The mystery was finally within reach. Pal and Ghosh's work is the best explanation yet for the gravity hole, tying together geology, computer models, and seismic data. But in science, no case is ever truly closed. Some researchers point out that computer models are simplifications, and the mantle's true structure is still partly unknown. The simulations don't perfectly match every detail of the gravity hole, hinting at other factors at play. Ongoing research is refining the models and searching for smaller structures that might contribute. The plume theory is a huge leap forward, but it's not the final word. Future scientists will use better computers and sharper data to fill in the gaps. The Indian Ocean gravity hole remains a natural laboratory for exploring Earth's deepest mysteries. The Indian Ocean gravity hole is more than just a solved puzzle. It's a window into Earth's restless heart, a place where the mysteries of our planet come alive. This vast anomaly, hidden beneath the waves, invites us to look deeper and ask questions about the forces that shape our world. It shows that our planet is alive and dynamic, with continents drifting slowly over millions of years, oceans rising and falling, and plumes of molten rock surging upward from the deep mantle. These movements are not just ancient history, they are happening right now beneath our feet, constantly reshaping the face of the Earth. The same powerful forces that created the gravity hole are responsible for moving continents, building mountains, and triggering earthquakes. They remind us that the ground we stand on is never truly still, but part of a vast, interconnected system of energy and motion. By solving the mystery of the gravity hole, scientists have deepened our understanding of plate tectonics and the churning mantle below. Their research helps us see how the invisible processes beneath the surface shape the world we know, and how much there still is to learn. It's a powerful reminder that ancient events like the sinking of a lost ocean millions of years ago still influence our world today. The scars of these events are written across the ocean floor, shaping the landscapes and ecosystems we see now. The gravity hole connects us to Earth's epic past and its ongoing evolution. It's a living link between the dramatic changes of yesterday and the transformations still unfolding today. Every feature on our planet has a story to tell, written in the layers of rocks, the movement of oceans, and even in the subtle pull of gravity itself. These stories reveal the incredible history of our world, waiting to be discovered by those who look closely. So, next time you look at a globe, remember, it's not just a map, but a living snapshot of a planet in constant motion. Every mountain, valley, and ocean is part of a grand, ongoing story of change. The Indian Ocean gravity hole stands as a testament to human curiosity and the wonders still waiting to be discovered. It shows that even in the age of satellites and supercomputers, our planet holds secrets that can surprise and inspire us. Our world is ever-changing, and the adventure of exploration never ends. With every discovery, we deepen our connection to this wonderful living planet, and the journey is only just beginning.